So we finally reached the end of the year, and we can all agree we've learned a lot. But do we really understand and know how to apply all of these concepts? Will all of the materials we've learned prove to help us in the future? For those of us who are still unsure, this video is perfect for you. We will be applying various mathematical concepts we learned in linear algebra and multivariable calculus to a creative real-life scenario. Let us time skip back to the Victorian era. In London, England, our favorite resident detective Sherlock Holmes had been requested to solve an interesting case from a rich client, which he explained to his partner Dr. Watson. The client is an ardent animal lover and a successful cat breeder. A number of weeks ago, an entire litter of her kittens were mysteriously kidnapped. In the span of that time that followed, the Scotland Yard had been able to recover nearly all of them scattered about various locations in London, except for 2. Now the client was desperate with worry, and had come to Holmes as a last resort. Watson found this all to be very perplexing. How could they possibly find the 2 kittens without knowing the identity of the kidnapper? Elementary, my dear Watson, Holmes replied. Using his powers of deduction, he had already long ago succeeded in pinpointing the suspect's identity. The likely criminal was a renowned physicist who lived outside the city on the moor. The physicist was famous all throughout the land for his hatred towards cats, and often acquired said animals for his many experiments. Having paid a servant all this at the physicist's estate to give him information, Holmes's suspicions were soon confirmed. The evil cat-hater had created a Ruby Goldberg machine with the end goal of flinging a rectangular cardboard box with one of the kittens inside into another box containing its siblings, and using their combined speed to compress a secret lever. The lever is designed to drop a gigantic electric cage with an open circuit on top of the kittens. The impact of the fall will allow the switch to close, forming a rush of current, which would ultimately electrocute the unfortunate animals. Holmes and Watson decide on sneaking into the castle in the dead of the night and replacing the panic-stricken kittens with stuffed animals. In order to accomplish this, they must use the power of mathematics to take into account a number of key factors. In order to create accurate replacements for the kittens, they must determine the mass of each kitten. In case something goes wrong, and they must resort to altering the settings of the Ruby Goldberg machine, they must also determine the speed required to compress the lever. In case something else goes wrong, and they come into contact with the electric cage, they must also find the amount of current running through each branch of the circuit. Finally, for their escape path, they must determine the path of steepest descent of the cliff. Fortunately, the infiltrated spy was able to steal one of the physicist's lab notebooks, which contained detailed plans of the design of the Ruby Goldberg machine. The blueprints included details about one of the key circuits in the electric cage and measurements of the boxes into which the kittens would be placed, as well as the default velocity settings. In his notes, the villain seemed to have also calculated the density functions of each box with the cats inside, assuming both boxes are bound in the first quadrant by the 3 coordinate planes. Unfortunately, he had left no record of the kittens' masses. Watson was crestfallen. Of what use was the lab notebook if it didn't contain the kittens' masses? Now the evil scientist would know instantly that something had gone wrong when they carried out the rescue mission. Holmes, however, was not worried in the least. Elementary, my dear Watson, he said. Can we not use triple integration to determine the masses? We have nothing to fear when the marvels of weighing calculus are on our side. Watson, who had majored in medicine, not mathematics, watched with curiosity as Holmes pulled out a TI-89 calculator and a pencil. To find mass, let ρ equal the mass density of an object. If dm equals the approximate mass of a small piece of that object where x, y, z is a point within that small piece and dv equals the volume of dm, then dm equals ρ times dv. This means that the function ρ times dv is equivalent to the mass sample of the object. Integrating both sides yields an expression for the total mass of the object. As such, triple integrals can be used to find the masses of objects with a non-uniform density. In this case, as the dimensions and mass of both boxes have been given to us, we can easily graph and solve for mass using the density functions of the boxes containing the kittens. Upon finding the mass of the kittens, our next task is to find the center of mass of each kitten and box combination, which is a vital piece of information needed to create stuffed animals of the same proportions. Finding the center of mass of an object is conceptually simple, but takes a lot of work. To find the xy coordinates for the center of mass, we must take the triple integral of the density function multiplied by z with respect to x, y, and z, and divide it by the mass of the kitten. To find the xz coordinate for the center of mass, we must do the same except multiply the density function by y. Finally, to find the yz coordinate, we must multiply the density function by x. The next task was to find the final speed of the boxes. In case something went wrong and they were unable to replace the kittens with the stuffed animals, Holmes and Watson planned on changing the default velocity settings of the machine so that the combined speed of the two boxes would not be sufficient enough to compress the fatal lever. Watson, who also did not pay much attention in physics in his college days, was stumped yet again. Holmes, however, had another idea very similar to his previous one. The equation for a perfectly inelastic collision allows one to find the final velocity of two colliding objects if given the masses and initial velocities of said objects. Since the evil cat-hating physicist recorded the position functions of each box and cat mass assembly in his notebook, Holmes was able to calculate the time of the collision. To determine when the box-kitten assemblies would collide with one another, Holmes set the two position functions equal to one another and solved for time. He then found the final velocity functions of each box and kitten combination by taking the derivative of each position functions. Next, he plugged in the time into the velocity functions to obtain velocities of each box-cat assembly right before they would collide. Finally, he was able to plug these initial values into the linear momentum formula to solve for the final velocity. The next step was crucial in case something went very wrong and the scientists managed to drop the electric cage on top of them during the rescue mission. Holmes decided it was best to also calculate the amount of current running through each branch of the circuit. If the amount of current turned out to be lethal after all, they would need to bring protective equipment. A light went off in Watson's head. Not too long ago, he had heard of a famous German physicist who had figured out a way to easily compute multi-loop circuits. A circuit containing only one battery is relatively easy to solve. Most of the time, you can add up the equivalent resistances of the resistors and solve for the missing variables using Ohm's law. However, things get more difficult when multiple paths and multiple batteries get involved. Like resistors, it is possible to add up multiple batteries into a single equivalent battery. However, in most cases, the batteries are located in different branches of the circuit, which makes this sort of analysis extremely difficult. In such a case, it is advisable to use a set of guidelines called Kirchhoff's rules. Kirchhoff's junction rule states that the amount of current entering a junction equals the amount of current exiting that junction. A junction is simply an intersection of multiple wires. Kirchhoff's loop rule states that the sum of all potential differences around the complete circuit loop is zero. Using a combination of these two rules in Ohm's law, one can easily determine the amount of current running through each branch of a multi-loop circuit. Let's take a look at our circuit. We can tell at first glance that this cannot be solved with Ohm's law alone. A closer look at the different branches reveal there are a total of 5 different current values on the diagram. Since the circuit is made up of 5 different wires, we do not know which direction each current is running, so we will make an educated guess for each. We will be able to determine the true direction of the currents through signs after we finish calculating these currents using Kirchhoff's rules. For instance, if the final answer has a negative sign, it simply means that our initial guess was wrong and that the current was flowing in the opposite direction. The signs do not in any way affect the magnitude of our current values. Now that we've identified the currents, our next step is to make loop pathways to follow so that we can apply Kirchhoff's loop rule. Again, as with the direction of the currents, where you wish to draw the pathways is up to you. Make enough pathways so that every wire is included. At least once. In our case, we need only 3. Our next step is to apply Kirchhoff's junction rule. We will pick up two junctions from the circuit and make equations based off of the junction rule. For instance, at the first junction, J1, currents 1 and 3 are entering the junction and current 2 is exiting. So our equation could be current 1 plus current 3 equals current 2. We will do the same with another randomly chosen junction. Next, we will turn our attention back to the loop pathways. For each loop, we will apply Kirchhoff's loop rule, which states that the net potential difference around a loop pathway is 0. The result should yield an equation with multiple unknowns that represents the current values. We will apply the same process for each loop we have made until we have enough equations to solve for the 5 unknowns. The result was a mess, at least it was to Watson's honest opinion. The system of equations that was left to be solved was not a pretty sight to behold. Holmes was undaunted. "Elementary, my dear Watson," he said. "Can we not use Gaussian elimination to solve for the current values? We have nothing to fear when the wonders of Sherlock linear algebra are on our side." Again, an utterly confused and fascinated Watson watched on as Holmes pulled out another sheet of paper. Gauss-Jordan elimination is an effective way to solve a complicated system of equations. We will put our equations into a matrix. Using multiple row operations, we will convert it into its upper triangular row echelon form. This is its forward space. We will complete the process by reducing the matrix further into reduced row echelon form. This last step is called the backwards phase. We can see that the current values yielded from this system of equations are all substantially larger than the amount needed to severely impair or even kill a human, which is 1 milliamp. As such, it is definitely advisable for Holmes and Watson to bring along protective equipment on the rescue mission. Finally, all that remained was to find a path for their escape route. The cliff upon which the evil physicist's castle was built was rocky and perilous. However, Holmes decided it was absolutely necessary that they take the most efficient path, as it was rumored that the cat-hating scientist kept a bloodthirsty hound as a watchdog. Watson was starting to get irritated. After all, the sheer amount of math displayed so far seemed exhausting to him. Fortunately, the infiltrated spy, who was as much of an animal lover as their client and was willing to go to extraordinary lengths to ensure that the kittens would be rescued, was all too happy to approximate a function representing the cliff. First off, in order to help visualize the problem, we will graph the given function. Our final task is to find the path of steepest ascent or descent of the mountainous region, assuming that the castle is located at the peak. The gradient is a vector whose components are made up of the partial derivatives of a function. It represents the rate of change of a function and is used for many different purposes, such as computing linear approximation, finding the exactness of a function, and identifying the path of steepest ascent or descent of a function, which is what we will be using shortly. Solving for gradient is a relatively simple process. All one needs to do is to find the partial derivatives of a function and convert it into a vector-valued function. Looking at the function given to us by our spy, we can see that we will need to use quotient rule to find the partial derivatives. Once we find the partial derivatives of f with respect to x and y, all that is left to do is plug in the starting position values into each partial derivative and solve. In this particular case, the starting location is at -5, 2.88, 0. Finally, all that is left to do is to plug these values into our vector form. In order to find the path of steepest descent, we would simply have to switch the signs. Night fell, the moon had risen to its highest parabolic point, and the inhabitants of London slept peacefully. That is, everyone but Sherlock Holmes and Dr. John Watson, finding themselves in Excel-sized FedEx boxes in the midst of stacks of physics textbooks and empty cages. They had waited for the hour to arrive. Now would be the time to determine the fate of the kittens. Watson had remembered to pocket his scalpel and was therefore able to free Holmes and himself from the unsuspiciously enlarged boxes. They slipped past the horrific-looking crates and made their way down the aisle in search of any last signs of life. There they found the 2 smaller FedEx boxes, each containing a small kitten that matched the description of their heartsick owner. The kittens commenced their purrs, using his pipe and Dr. Watson's watch and chain as lockpicks. Holmes opened the crates and prepared to transfer its contents into a burlap sack that Watson had brought. However, the ungrateful cats became very upset at the sudden light exposure, and each let out a loud meow of protest. Suddenly, a deep growl forced the bars on the cages to tremble, resulting in a clattering sound. Heavy footsteps shook the towers of textbooks until they fell over, and a shadow on the wall consumed the little light that had been there. Finally, a paw came forth from behind a door. It was the evil physicist Dr. Kames who entered the room, strapped to the seat of a machine that resembled a gigantic metallic bloodhound. The stunned kitten saviors were paralyzed by this overwhelming sight. Then, in an extremely high-pitched voice, Kames spoke.
"Let the cat out of the bag, Holmes. Hand over the kittens."
Reminiscing about their last encounter of Kames, Sherlock remembered that Kames had been partially blinded by Sherlock's poison cocktail. His overall senses had been weakened. Hence, Kames couldn't see well enough to distinguish a stuffed animal from a real kitten, especially if they had the same masses and general proportions. Holmes pushed the bag which contained the stuffed animals towards the villain. As he did so, he noticed the trapdoor right below the enormous paws of the monstrous machine dog and the giant circuit cage right above. Kames took the bag, not knowing that they weren't the real cats.
"Very well,"
said Kames.
"Since you have cooperated so well, I shall let you choose which way you will end your time in this world."
In a soft but confident voice, Holmes replied, "I would love to stay and chat, but I'm positively sure that that'll end up to be a major catastrophe on our part." And with this, he pushed the lever that released the circuit cage. The cage fell on Kames and his metallic dog and fried the electronics, causing the machine to fall sideways with an explosive clatter. Holmes and Watson used their chance and fled with the kittens through the trapdoor that led them to the downward tunnel of the steepest descent. As the sun rose gloriously over the horizon, Holmes and Watson safely entered the streets of London, and at last the kittens were returned to their overjoyed owner. The end. Heavy footsteps shook the towers of textbooks until they fell over, and a shadow on the wall consumed the little light that had been there. Finally, a paw came forth from behind the door. It was the evil physicist Dr. Kames who entered the room, strapped to the seat of a machine that resembled a gigantic metallic bloodhound. The stunned kitten saviors were paralyzed by this overwhelming sight. Then, in an extremely high-pitched voice, Kames spoke.
"Let the cat out of the bag, Holmes. Hand over the kittens."
Reminiscing about their last encounter of Kames, the stunned kitten saviors were paralyzed by this overwhelming sight. Then, in an extremely high-pitched voice, Kames spoke.
"Let the kittens out of the bag, Holmes." Wait, that was bad.
The cat out of the bag.
Then, in an extremely high-pitched voice, Kames spoke.
"Let the cat out of the bag, Holmes. Hand over the kittens."
Reminiscing about their last encounter with Kames, Sherlock remembered that Kames had been partially blinded.
I was hiding my face. I hid my face, okay? Okay. That was not my fault. That was not my fault. That was not my fault.